Okay, we're going to continue with homework 37, problem 9.4-4. All right. Okay, so this problem is similar to the last problem. We're just going to jump right in. Okay, let me start by drawing this out. So, wall, we've got cantilever beam, looks like that, and then you've got a load on there. Load Q, let's push it down, Q. And then you have a spring right here. Okay, obviously there's a reaction force RB right there, and we have a moment A. Okay, so I'm going to start this out by just drawing the shear bending diagrams. So you're going to have a shear diagram that looks something like that. Bending that looks something like that. Let's see if I can make it fit. Okay. So that's bending, that's shear. You've got shear diagram because you just got a Q, so you've just got that line right there. It's a cantilever beam, so your moment should go down to 0 right there with an applied moment right there. Okay. So we're gonna just write out a couple things that you just get from solving. So you're gonna have the spring factor K on there with deflection, which is this sigma, so we can call it sigma B. And they've given us what K is. They say K is equal to 48 EI over L cubed. Let's see. Should be all the information that we need. Okay, so I'm just going to jump ahead and we're going to start this. All right, so remember we're just going, same thing as last time. You integrate down, going from the load to the shear to the moment to the slope deflection to the deflection. Okay, so if we say that our shear is equal to negative Q integral, that just leads us to Qx plus C, which if we solve for the shear, if we look at that diagram initially, we see that at zero, it's 0, so we can say that our C value is just going to be 0. Okay, so now we do the moment one, and we can say that the moment is the integral of negative Qx, right, which is going to get us a negative Qx squared over 2 plus C. Okay? So we can say, looking back at this diagram, that at length L, our moment is 0. So if we go back to this and we say at L, when our moment is equal to 0, at length L, so negative Q L squared 2 plus C, then our C value comes out to be QL squared over 2. Okay, pretty straightforward so far. And now if we go into slope of deflection, remember it's the EI, and then d prime is equal to the integral of negative QX squared over 2 plus QL squared over 2. Just have enough room, which is going to equal to a negative QX 6 plus XQL squared over 2 plus C. Okay, a new thing. So if we look at this, slope of deflection takes a little bit of thinking. So now if we go back, to look at this, okay, so where is it going to be equal to 0? Now it's kind of hard to see here, but let's see. So if I was to move this guy along, right? If he was to say to go downwards, which is what's going to happen because we have a downwards Q, right? Still at the very start, it's going to be stationary, and it'll probably move a little bit downwards, pressing down that spring, right? But right here at the start, our deflection is going to be equal to 0, right? Which means if we go to this one, our C just gets crossed out, right? Which makes things pretty easy for us. C is just equal to 0. Now if we move on, we have our, so we just did our slope of deflection, now we're doing our deflection. Okay. So that is now going to be, now it just goes to one of these guys. So our deflection is equal to the integral of what we just solved for, 6 xq over 2. Okay. So we solve that out, we get negative qx to the fourth over 24 plus x squared ql squared over 4 plus c. Okay, so now if we look at this, if we go back, there's no, with the deflection, there's going to be deflection in everything, right? So we're kind of at a tricky point. In all the previous ones, we've been able to just say at 0, it's 0. What we can say that, let's see, so if we just write this out right here. So we can say, though, that the deflection is going to equal our reaction force, RB over K, right? Because we can see from this, the standard spring formula right here, right? The sigma is deflection, so you could have read it like that as well, okay? So that's just manipulating the formulas around. So now if we go back here, we have this equation. We can say RB over K, and we know our distance is L because that's where the spring is located, right? So now, let's see, if we start plugging a couple things in, we got negative Q, L, 4 plus L squared Q L squared over 4 plus C. Okay, and then we're looking at this RB over K. Now if we can jump back and forth a little bit, we know what K is, right? So we can plug in our values for K, and we can solve for our reaction force, which if we solve for RB, we find that it just gets us Q over L, right? If we were just to look at this formula right here, this value right here is just Q over L, right? Which means that it's just this K value is over this value. Okay, so now if we jump back, we can put these in more terms that we understand, that we can use to solve, really. And now I'm just going to simplify. Let's see. I'm just going to plug everything in. So now it's Q L over 4 EI is equal to that whole thing that we just solved for. All right. So to do. And now, if we solve for C, just go to the next page, C is going to end up being, it's a lot of simplifying, so I'll write out the intermediate step, 48 plus, hopefully I'm writing these down right, 48 minus 12 QL over 48 EI. Now we're going to go in and we're going to simplify all that, plug in all the values we know that c is equal to 48 ei. Okay. So now our equation for deflection, which is also that guy right there, is equal to negative qx, 24 ei. I've also moved that ei that used to be there, so there's an ei in the bottom. Ql squared over 4 ei minus 11 and 48 ei. Alrighty, so that is our formula. I think also another thing that they're looking for is, let's see, so this is one of the answers. Box that, and now another thing. So something else that they are looking for is actually they have that theta b, which is just equal to our slope of deflection at L. Okay? So if we bring up that equation that we had in the past and we plug in an L to it, negative Q3, 6 plus QL 3 over 2, right? If you're wondering where I grabbed that from, let's just go back a little bit. That was this equation right here from our slope of deflection, right? I just took that and plugged in an L. So now looking forward, we have that. It's nice that we have the same amount of L's, so it's easier to add. We just, the same denominator, and we're gonna plug in some stuff. And, oh, I forgot the EI that's on there. Okay, so now if we plug in everything, solve for it, we're gonna get Q2L cubed over 6EI. Which if we simplify a little bit more, the 2 and the 6, you get QL over 3EI. All right, so we have that value right there. And then one thing to catch yourself is there's also a negative sign right there. And I probably, well, with the back of the book, it's negative sign. I probably switched my y axis as opposed to what the book does, but you can just look at the problem and you can look at it by inspection as well, right? Because you have that force Q that's pushing down on it evenly, right? So it's going to end up being pushed downwards, right? There's not really a way that it is going to curve up, right? So you can also say, you know, by inspection that slope is going to be negative. So thereby also our angle is going to be negative. So that is the answer to that.